So for this last part of the chapter, we're going to look at protecting groups. So protecting groups in chemistry is this term essentially what we're using to prevent some part of a molecule from reacting. It's literally doing as the name implies, right? It's protecting something. So we're going to look at a few different ways we can protect different functional groups. So we're going to look at alcohols, amines, and carbonyls in terms of how to protect them. So we've learned a lot of reactions in chemistry, right? We've learned a ton. And something that hasn't really come up is what if one side of the molecule reacts, but the other can also react, right? When we have to decide what way we want to do chemistry. And this happens in real life, right? This is a real problem that people encounter where they are unable to proceed with a chemical synthesis because they have a group that's interfering. So we're going to look at some ways that we can do this and examples of why that matters. So for this first example here, right, we have something as an alcohol and a carbonyl, right? But let's say we're doing a reaction where that's problematic. So notice down the road here, we're doing this Grignard reaction, right? Grignard can react with alcohols as well as carbonyls, right? They can deprotonate those alcohols. So that makes it kind of problematic. So we have to protect the alcohol, meaning make it non-reactive, right? That's kind of something else that we could call it, right? These protecting groups are making these groups non-reactive for the most part. So how do we do that with alcohols? So let's say we have our alcohol, right, our OH group down there. Something we can do is we can react it with with this group here called TMS chlorine. And TMS stands for trimethyl silyl. And so the silyl-protecting group, right, is a silicon group essentially. And silyl-protecting groups in general tend to have this general format of a silicon atom and then 3 different alkyl groups attached to them, and then usually something like chlorine or whatever as a leaving group to affix it to the alcohol, right? And essentially it's proceeding through a SN2 reaction. You see in our conditions here, we have that trimethyl silylchlorine, and then we have this triethylamine here. This is just a base, right? So triethylamine is this bulky base, actually. So it's a bulky base, so it's not going to act as a nucleophile. It's only going to make things a nucleophile, right, like that OH. So over the course of the reaction, right, we have our alcohol that has been deprotonated, right, by the triethylamine, and it's going to just simply attack the it's going to attack the silicon atom here. Right, make the chlorine leave. Remember, silicon is right below carbon on the periodic table, so it has very similar properties to carbon. It's just a bigger carbon that has, access to more electrons, but it effectively performs the same. So notice now, right, we have our protecting group here, right? The oxygen is protected. It can't do chemistry anymore. It can't act as a nucleophile. It can't be deprotonated or anything like that. It's already all set. So now, when we do our Grignard reaction, we can do it as intended, right? Turning our our carbonyl just into the alcohol, right? Just doing our standard Grignard. The last step here, we have this group, this tetrabutyl ammonium fluorine. So this is a fluoride reagent. And all this step is saying is that we are deprotecting the alcohol, right? This is removing the protecting group to go from our TMS oxygen back to our just regular alcohol. So this is just a deprotection step. These fluoride reagents are particularly good at removing silicon groups. So that's all that's doing, right? The big takeaways here, right, is that we can use this TMS chlorine and base to protect alcohols, and then, right, we can remove them afterwards to get back to our original alcohol. Next one we can look at is something we've kind of already seen. It is the protection of carbonyls, which we looked at earlier in the last chapter, right? Taking carbonyls and then reacting them with, right, these diols to make these right, acetals. So this reaction, again, we've already done, right, with this tosic acid and our diol here, right, both sides are reacting, right, both those alcohols are reacting with our electrophile here to get to our cyclic acetal. So this protects it, right? And the big reason why we want to do that, right, is, again, our carbonyl here is electrophilic, and we also, right, notice we have an alkyl halide here. So if we want to do an SN2 reaction on this alkyl halide, as we can see later down the road, right, this SN2 reaction has occurred, that would be problematic if we had a carbonyl, because this would also react with a carbonyl. So by protecting the carbonyls we've done here, right, to make our cyclic acetal, right, this is no longer, right, the carbonyl is no longer reactive. Right, it's not a carbonyl anymore, but we've made it a non-reactive group, right? We've made this a protecting, we've added this protecting group, so it is no longer reactive. And the last step, right, as we've seen before, right, in that previous chapter, we can deprotect these acetals using these deprotecting conditions, right, just these acidic conditions here, which transforms the acetal back to our carbonyl. Right, and again, these protecting groups are important because it's making these once reactive groups, right, this carbonyl is pretty reactive, into something that is much less reactive, right? So that's really important. And the last one we're going to look at here is protecting amines. And so we can protect amines in a very similar fashion, right? We're taking an amine and we are adding, right, this acyl group to it. And what this does is, right, with this amine protecting group, right, we're essentially making an amide, right? And by doing that, we're making it no longer reactive, right? So the amine can no longer act as a nucleophile, right? Because, right, the amide, nitrogen and amide, or amides, right, the lone pair is in resonance, meaning, right, the nitrogen is no longer nucleophilic. Right, so it can no longer act as a nucleophile. Right, so with amidal protected, we can do, a whole manner of things to it. Like, for example, just a simple nitric acid addition, right, to add a nitric group to our benzene here. And then once we finish what we want to do, we can go ahead and remove the amine, or remove the amide afterwards. So we can just do hydrolysis, right, which we learned about earlier in the chapter. So this is our deprotection step, if I can spell correctly. Right, this is our deprotection step. And so we're taking, right, again, the amide and just turning it back into an amine. And we're also generating, it's not really important, but we're getting a carboxylic acid here as well, right? Because it's turning that amide into a carboxylic acid, right? But we're leaving the amine behind. So this is a way that we can go from a nucleophilic amine, right, into something that is, right, not nucleophilic anymore. So nitrogen cannot react as a nucleophile. Another potential protecting group we can use, and it does the same thing, if we start from the same starting material here, there's another reagent we can add called, it's called BOC2O, and it adds something called a BOC group to an amine. And the BOC group is this large thing here. So it's this ester with a terp butyl group. And so BOC2O, right, is just this whole thing, but, right, you can already tell it's kind of a pain to dry everything out. So this is BOC2O. And the BOC group, right, is just attached to the nitrogen now, and now it is essentially doing the same thing, right? The nitrogen is no longer nucleophilic, right? And then to deprotect it, you would just add an acid, right? So we use acidic conditions to to deprotect. And we get back to our amine. Right, so these are two very viable ways to protect amines here. And we'll look at some examples in class about using protecting groups and when they can be important.